Welcome back. Now in this session we can start chapter number 4, which is very important chapter. I can say relatively with respect to other chapters, because with respect to GATE examination more weightage from Opamp circuits. Okay. Now chapter number 4. Opamp and its applications. Okay. Now the first topic, Opamp. After completing Opamp, we will see the applications of Opamp. Okay. What is there inside Opamp, and what is the block diagram of Opamp, and what is the first stage, second stage, third stage, etc. Right? Those things we will see from the topic called Opamp. Okay. Now I think from BJT amplifiers, FET amplifiers, we got to know that the final amplifier are the best amplifier what we can get from your RC coupled CE amplifier and then RC coupled CS amplifier, right? And we have seen the frequency response of RC coupled CE amplifier, and the same frequency response is expected from RC coupled CS amplifier. The limitation of RC coupled CE amplifier is what? The low frequency signals are not able to process with the gain, whatever gain we are expecting, which is mid-band voltage gain. Now, but if you take Opamp, if you ask me the definition of Opamp, the definition of Opamp is, it is high gain, it is going to provide high gain, direct coupled, or I can say anything is fine, direct coupled high gain differential amplifier. It is nothing but this is direct coupled, not RC coupled, it is direct coupled high gain differential amplifier. Basically your Opamp is differential amplifier, but having huge gain because of multi-stage differential amplifier followed by a common emitter amplifier, and it is a direct coupling. There is a reason to have direct coupling. What is the reason to have direct coupling? I'll explain those things. And how to get high gain, I'll explain. And what is differential amplifier, I will explain. Right? Therefore, 3 things I need to explain. And out of these 3, I think you know already what is high gain. How to get high gain? Multi-stage configuration. If you have multi-stage amplifiers, you will get high gain. Right? Take the definition. This is very important. Then we should know what is direct coupling. We should know what is differential amplifier. And we should know the cascading of the stages. Multi-stage configuration. That is what is going to give you high gain. Okay? Okay, let me explain, right, through block diagram. Write down Opamp block diagram. See, we want ideal amplifier. When I say ideal amplifier, remember we want voltage amplifier. This is what is called voltage amplifier. By default, we want voltage amplifier. People developed a circuit, right, a specific circuit, a special circuit, that is nothing but op-amp, but it is voltage amplifier. But we can get current amplifier using op-amp, trans-conductance amplifier using op-amp, trans-resistance amplifier using op-amp. Okay. Now, if you see the block diagram, right, then I'll explain one by one. The first stage will be differential amplifier. Just listen. The first stage is differential amplifier. And it is having two inputs, but I told to have very high input impedance, this is what is having Darlington pair. This is having Darlington pair. This is Darlington pair. Because we have two inputs, you will have two Darlington pairs. Then this is what is the input. Okay. Then differential to signal conversion is there inside, and to have more gain, one more amplifier, you can say CE amplifier. Okay. Now we have again final, this is what is a buffer amplifier. What is buffer amplifier? Again your CC amplifier. Okay. And this is what is our output. Okay. Therefore, how many inputs you have? You have two inputs. Let us say this is V1 and then V2. That is what is your V0. Therefore, this is what is the block diagram, which is what is present. This is what is your op-amp. Let us say this is what is your V0. Okay. Actually, we had seen this, right? You remember when we see BJT amplifiers, I gave you one conclusion. If you want voltage amplifier, we want very high input impedance, very low output impedance, and very high voltage gain. To have very high input impedance, we used Darlington pair at the input, and to get very low output impedance, we used CC amplifier at the output. To get more gain, we used multi-stage CE configuration, right? But instead of CE amplifier as the first stage, now it is nothing but differential amplifier. Then because two inputs, two Darlington pairs, therefore this is what is our op-amp. Take the block diagram. Therefore, what is input impedance of op-amp? Infinity, you can say, because of Darlington pair. What is output impedance of your op-amp? Almost zero because of CC amplifier. Therefore, you can say this is nothing but CC amplifier. Even I am saying buffer amplifier, this is nothing but CC amplifier. Okay. Then this is our CE amplifier, which you know already. Differential amplifier is also CE amplifier, but I will explain the speciality of differential amplifier. Then I think it is already done. We had seen already what is Darlington pair. We had seen already what is CE amplifier. We had seen already what is buffer amplifier or CC amplifier. Only the block which we did not see is nothing but differential amplifier. Therefore, let me explain. Okay. Now, if you ask me, right, what is the voltage gain of Darlington pair? Approximately equal to 1. What is voltage gain of differential amplifier? Let us say A1. And what is voltage gain of common emitter amplifier? Let us say A2. What is voltage gain of buffer amplifier? Approximately equal to 1, right? Therefore, if you ask me the input impedance, both, right? Both input impedance, right? Let us say both in the sense, okay, both, it is almost infinity. And what is output impedance? With respect to output, the impedance seen into output port, okay, that is nothing but almost 0. And what is the voltage gain? Here the voltage gain of this is nothing but the voltage gain. This is what is approximately equal to 1. And here the voltage gain, let us say this is what is AV1 and this is what is voltage gain AV2, and the voltage gain this is having approximately equal to 1. Then overall what is your voltage gain? Overall this is what is having voltage gain. This is what people call it as AD, that is nothing but differential gain. I'll explain what is differential gain that is associated to differential amplifier, or I can say the difference of your input signal will be amplified. Let us say the difference of your input signal, this is nothing but your VD, right? Then your AD is nothing but, your V0 is nothing but, AD is nothing but AV1 and AV2. Therefore, this is AV1 and AV2. Then if you ask me what is V0, your V0 is nothing but AD into VD. Means your op-amp is going to amplify, difference of your input, because that is what I am going to explain later on, because that is because of differential amplifier. After this I am going to explain what is differential amplifier, because we should know only differential amplifier and how to get direct coupling. Those 2 points if I explain, I can say op-amp part is over, but that will take some time. Okay. Therefore, if you observe clearly, AV1 into AV2, that is overall differential gain, and whatever signals you are applying between V1 and V2, the difference of V1 and V2 is amplified, and that is what you get. V0 is equal to AD, the differential gain into VD. There is something called common mode gain. Common mode gain is nothing but, if you apply the same signal for both V1 and V2, that signal will not be amplified. Only the difference between V1 and V2, whatever you have, that signal will be amplified with the gain of AD. Okay. Now if you ask me, right, with respect to the 4 AC parameters what we had seen, right, the characteristics, right, if you see the characteristics part, characteristics, okay, ideally what do you want? Ideally I want voltage gain to be infinity or very high. Ideally I want input impedance to be infinity. Ideally I want output impedance to be 0. Then what is current gain? It is undefined. Don't say infinity. It is not applicable. Why? Because what is your input current? Current entering into your op-amp. Because input impedance is infinity, current entering into your op-amp is 0. If current entering into op-amp is 0, input current is 0, even though you have some load current, when you connect load here, even though there is load current, because there is no input current, we should not define current gain. Therefore, current gain is undefined. Therefore, we are mainly looking for very high voltage gain. When I say very high voltage gain, AB is nothing but here basically AD. We are looking for very high differential gain, very high input impedance, very low output impedance. Current gain is undefined. Therefore, basically this is nothing but it is for voltage amplifier. Therefore, all these things are for voltage amplifier. Therefore, what is your op-amp? Op-amp is basically voltage amplifier. Okay. Okay. I'll explain what is differential amplifier. Okay. Then after explaining differential amplifier, I will explain what is direct coupling. Then if these two are done, I can say over. Okay. Take this. Practically current voltage gain is not infinity. Practically if you take IC741 op-amp, I'll give you the list later after explaining differential amplifier. Practically the differential gain is 2 into 10 to the power of 5 means 2 lakhs. And input impedance will be in the order of tens of mega ohm. Output impedance will be in the order of tens of ohm, less than 10 ohm or less than 20 ohm. Then you can say it is almost ideal. Even though gain is 2 lakhs, you can treat it as infinity only. Okay. Therefore, this is what is open loop op-amp. Open loop in the sense nothing is connected in the feedback, right? Just input to output, open loop. This is what is open loop op-amp characteristics. Using this open loop op-amp, we are going to have so many applications. We are going to connect in positive feedback, negative feedback, comparator action. So many things we are going to see. Those are all nothing but applications of your op-amp. I think out of 3 important terms of op-amp, direct coupled, high gain, differential amplifier, you know high gain because of these 2 stages you are getting gain. Because of buffer amplifier and because of Darlington pair we are not getting gain. We are getting gain because of differential amplifier and common emitter amplifier, right? Then high gain only you understood because of 2 stages. Now I am explaining what is differential amplifier. Means I am going to explain the purpose of differential amplifier, then we will see direct coupling action. Or I can combinedly explain differential amplifier along with direct coupling, then we will get the definition, complete definition of op-amp. I'll give you 30 more seconds, then we will see differential amplifier. Remember, we don't want to amplify common mode signals. What is common mode signal? The signal which is common for both V1 and V2. That is what is called common mode signal. Mathematically, people define it as V1 plus V2 by 2. The signal which is common for both the inputs, that is what is called common mode signal. Mathematically, V1 plus V2 by 2. We want to reject common mode signals. That's why this is defined with something called common mode rejection ratio. We will see all those things later, but let me complete. Okay. There are 23 AC parameters, or there are 23 total parameters associated to your op-amp. Out of 23 parameters, I think 4 only I have written here. Then if you continue, we have 23 parameters. Okay. Done? Okay. Now, I can explain little bit about direct coupling that we can incorporate into differential amplifier, then we will get the action. Okay. Now, before going to direct coupling or differential amplifier, if you consider RC coupled CE amplifier, RC coupled CE amplifier or CS amplifier, anything is fine, whether it is BJT amplifier or FET amplifier, right? What did we see? Just listen, don't write anything. And this is what your coupling capacitor and this is what your output. Okay. And load is connected. And here input is there. Okay. Now, what is the limitation of RC coupled CE amplifier? The limitation of RC coupled CE amplifier, if you take the frequency response and the gain whatever you have, right? We are not able to amplify the low frequency signals. The limitation is nothing but I'm not speaking about high frequency amplification, only speaking about low frequency amplification. Therefore, your gain, low frequency gain, therefore there is low frequency distortion. We are not able to amplify low frequency signals, right? Therefore, what is the reason? What is the reason to have low frequency distortion? Because if gain is not constant, that is what is called frequency distortion. But for low frequencies, we are having frequency distortion, therefore low frequency distortion. Now tell me, what is the reason to have low frequency distortion? I am not expecting high frequency signals to be amplified. At least I want low frequency signals to be amplified along with the mid-range of frequencies, right? Therefore, I want to improve the frequency response like this. I want to have kind of low pass filter, not band pass filter, right? Then how to improve this? But the frequency response, whatever you are getting here, I already explained. The reason is because of CB, CE, CC. Because of external capacitors, we are getting low frequency distortion, and because of BJT internal capacitances, we are getting high frequency distortion. How to improve it? Can you improve for this? Can you improve the low frequency distortion? If you improve, right, means we should not have CB, CE, CC. If you don't have CB, CE, CC, then it is not called as RC coupled CE amplifier. That is what is called as direct coupled amplifier. Therefore, what is the purpose of direct coupling? Purpose of direct coupling is to improve low frequency response, right? Then you'll get flat. Then how to take out? Directly can I take out? If I take out CB, take out CE, take out CC, output will be 0. Why output will be 0? Let us say, if I take out CE, your gain will reduce. That is one thing, but functionality wise there is no issue. Only performance or the gain of your amplifier is reducing. Therefore, that is fine. But if you take out CC, you will get DC plus AC. If you give DC plus AC to your output, DC plus AC to your output, then what will happen? Let us say loudspeaker, we should not give DC voltage to loudspeaker. We have to give only pure AC signal to the loudspeaker. If you give DC plus AC, we will not get any variation of diaphragm, which is what is there inside the loudspeaker to get this mechanical output. Therefore, we should not give DC output to the loudspeaker. We have to give only AC output to the loudspeaker. Therefore, how to get or how to give without this CC, because I want to block the DC, that's why we use CC. But without CC, I want to give only AC signal to the load. Can I give if there is no capacitor with this architecture? No. Similarly, if you take out the CB and then put directly input voltage, then the input voltage, DC voltage, whatever you have, that is what is overwriting the input bias voltage and then disturbing the functionality of your transistor. Therefore, when I say if you apply only AC signal, what is the average voltage? If you apply only the AC signal, average voltage is 0. Then on top of that, the signal whatever you want to amplify, that is what we are applying. Then the 0 voltage, if there is no capacitor, the 0 voltage you are applying directly, then the 0 voltage you are applying between VBE to the drop here. Then VBE is 0 and we are applying very small signal. To do not see amplitude distortion, we need to apply small signal. Then the transistor is entering into cutoff, completely gone. That's why I told V0 is equal to 0. I cannot do anything. Then what to do? Whatever 0 volt which you have from your AC signal, whatever 0 volt which you have in AC signal, that itself should act as a bias voltage. Then don't generate bias from VCC R1 R2, right? Then can I tell you one solution? The solution is to make it direct coupling. Therefore, what is direct coupled amplifier? Partial direct coupled amplifier. Partial direct coupled amplifier. Direct coupled amplifier. Okay, just listen here. At least I can remove this and this. How? Just listen. See how I am making it. Let us say this VCC is equal to 10 volts and the minimum voltage is 0. Therefore, what is your power supply rail to rail? 10 to 0. Now this is RC. Now I don't need output capacitor. I am just directly taking V0. I don't need input bias voltage. R1, R2 also not required. Fantastic. Your component, number of components required required to have the biasing and all decreased. Now directly I can give input voltage. This is what is my input voltage Vi. But the correction is now VCC is not 10, let us say 5. I need to apply negative voltage. That is what is, let us say VEE, which is minus 5 volt. Whatever 10 volts you have, 10 to 0, we need to apply like 5 to minus 5. Then what is the total voltage? 5 minus of minus 5, 10 volts. By defining negative power supply along with positive power supply, that will serve the purpose. How? Just listen. Therefore, this is what your RE. But still I need a capacitor, bypass capacitor. Let us say this is what is my bypass capacitor, CE. Now I don't need input capacitor, I don't need output capacitor. Why? Listen. You remember this is what I told. Means if you take a PN junction diode, I told, let us say this is 0.7 and this is 0, PN junction diode is conducting. That is what till now we used to do. VCC R1 R2 combination, R2 divided by R1 plus R2 into VCC is VThevenin, R1 in parallel to R2 is Rthevenin. That VThevenin is equal to drop across Rthevenin plus VBE plus IE into RE. That is what we used to do. We need some voltage to bias our transistor. But now therefore we need 0.7. Now what I am saying, the solution is, instead of defining other terminal 0, you define it as minus 0.7, you give input 0. If you give input 0, but still it is forward bias only. Because you are defining other terminal with negative terminal, even though you give 0, that 0 voltage will act as a bias voltage, then that is also making your PN junction diode forward bias. Exactly the same principle. Now tell me, what is your input DC voltage? Now my input DC voltage is 0 and the signal whatever I want to amplify, that is what I am applying. Now tell me, the 0 voltage whatever you are having, now this is 0, but your emitter is connected to what? Kind of negative voltage. Then this is nothing but what? NPN transistor. This is NPN transistor. P is connected to 0, but N is connected to negative voltage. Yes, then whatever it needs like forward bias, it will be forward bias. Therefore, remember R1, R2, VCC now not required. The input 0 voltage will be acting as a bias voltage. Therefore, we don't need input capacitors. Because earlier I told whatever AC signal you want, that AC signal should be coupled on top of the local bias what you have through VCC R1, R2. Right? That's why we used CB. If CB is not there, the DC voltage what you have in the input signal, that is what is overwriting the bias voltage what you set by VCC R1, R2, and it is making the transistor into cutoff state. Therefore, this CB is compulsory. But now if CB is compulsory, my frequency response is limited because of CB, CC, CE. Now, by defining dual power supply, plus 5 and then minus 5, then even though you are giving 0 voltage as input, that 0 voltage will be acting as a bias voltage. Something like this. The 0 voltage will be acting as a bias voltage because other terminal is defined with negative voltage. Now, coming back to output side. We want midpoint of rail to rail, right? What is midpoint of rail to rail? 5 volt and then minus 5 volt. Therefore, what is 5 volt? Highest power supply, 5 volt. Lowest power supply, minus 5 volt. Okay. Now what is mid voltage? Your mid voltage is 0. Your mid voltage is 0. Therefore, what is your output signal? Now your output signal is not having any DC voltage. Then do you want to block the DC signal? No. Earlier we used capacitor CC to block the DC what you have from transistor output, only pass AC signal to the load. Now I don't have DC. Therefore, whatever signal you applied here, right? Whatever signal you applied or whatever signal you want to amplify, don't write, just listen. Whatever signal, the small signal, whatever you want to amplify, now this is what is amplified, then you are getting at the output. Now directly without any capacitor, I can give it to what? I can give it to load because now it doesn't have any DC voltage. No need to block the DC. Therefore, input capacitor is removed, output capacitor is removed, but this resistor is compulsory and this capacitor is also compulsory if you want to get more gain. Ultimately, now I want more and more gain. If I want more gain, definitely this RE should be bypassed. You may say directly short it. If you directly short it, remember we cannot use it. Not only that, we want Q point stability. Therefore, RE is the one which is what is our feedback resistor. This is our feedback resistor. This is compulsory to get feedback. Therefore, this is what your feedback resistor. Feedback resistor, right? Feedback resistor, which is providing Q point stability. That is compulsory. Q point stability. Therefore, if RE is there for DC analysis, I don't want RE for AC analysis. We need to put bypass capacitor. When you put bypass capacitor, then again still I can say your frequency response is a little bit improved, but not completely, because we could not avoid CE. That's why I told this is partial direct coupled amplifier. Okay, take it. But how to avoid the RE, or how to avoid the CE, not RE, how to avoid CE in a different architecture way, using a different architecture, that is nothing but your differential amplifier. From differential amplifier, we are going to get that RE in a different way, then we don't need CE. Okay, that's what I'll explain. If that is done, the op-amp definition is over. Okay, take it. This is what is your partial direct coupled amplifier. If you ask me, CB and CC are removed. Okay, CB and CC are removed. But these are all, whatever we had seen, right, all are single-ended amplifiers. What do you mean by single-ended amplifier? Applying input with respect to ground, taking output with respect to ground. That is what is called single-ended. But differential amplifier is nothing but applying input between two terminals. Means difference of these two terminals will be amplified. That is what is our differential amplifier. That is the reason why your op-amp is having what? Dual power supply. Your op-amp is having dual power supply. Plus VCC minus VGE or minus VCC. You can write here the low frequency distortion due to what? Low frequency distortion due to CB, CE and CC. Now if you ask me the frequency response of this amplifier, still if you ask me, right, mod AV, it is improved but not completely. You can say it is improved but not completely. Therefore I can say improved but not completely. I am not speaking about high frequency response, that we cannot improve. To improve that high frequency response or to increase the bandwidth, we have to change the BJT structure or geometry. That is nothing but process, from one process to another process. That is technology scaling. We want the size of the transistor to be minimum, then the capacitances associated to the transistor will be minimum, then the frequency, the transistor frequency, or I can say the bandwidth will increase, or it can amplify high frequency signals as well. That is what is from one process to another process. For a given process, I cannot improve frequency response. I cannot take out the internal capacitances. That we have to live with it. Here this is improved but not completely. Now we want to improve, then make it flat. If you are able to make it flat, then problem is over. That is nothing but your differential amplifier, where we don't need CE. How to make it without CE, that is what we will see. Then it is done. Now a little bit theory has come. Till now we solved the things using mathematical analysis and solved the problems. Problems are always interesting because your brain will be so active with respect to pinpoint of values. If it is generic value like X, R1, RC, RE, gain, this, then our brain is not so active. Hope this is done. Okay. Now write down differential amplifier. Then after explaining differential amplifier, I'll explain how we don't know CE. Okay. Therefore, let me explain only differential amplifier by like 10 volts and then 0 volt. Okay. But remember, then after explaining differential amplifier with single supply, then later on if I incorporate dual power supply and without CE, that is nothing but your direct coupled differential amplifier. Okay, done. Now I'm going to explain why we don't need CE. Even we have dual power supply or single power supply, we don't need CE. Then that is what we are going to get from differential amplifier. Okay, let me rub it, then write down differential amplifier. Differential amplifier. It is going to amplify only differential signals. It will not amplify common mode signals. Okay. Now let me give you differential amplifier circuit. Circuit is actually minus VGE and plus VCC. Okay, that part we can do it later, but now I'm explaining why we don't need CE. Now we don't need CE because of this. Okay, let's see. And now this is what is your V1 and this is what is our V2 RC, and this is, let us say, V01 and then V02, and this is what is, let us say, I bias. This is what your bias current. Okay, using current mirror or whatever it may be. Okay, now this is what, let me call this as transistor 1 Q1 and transistor 2. Now if I speak with respect to, let us say, the VCC is equal to 10 volts and ground, this is what is 0 volt. I need to explain again DC analysis as well as AC analysis. Okay. Now, if you define only with 10 volts and then 0 volt, then we have to give some DC voltage. Actually, the DC voltage earlier using self-bias circuit, right? R1, R2 and all. Now, let me give directly the DC voltage from the source itself, whatever you want. That is what is called the DC voltage here and then the DC voltage here. Both the DC voltage will bias the transistors Q1 and Q2 in active region. Then your circuit or differential amplifier is ready for the amplification. That is what is called DC analysis. Okay. Then on top of the DC voltages we are defining, which we are providing the DC bias voltages externally. On top of those bias voltages, apply the signals whatever you want to amplify in a differential manner. Then it will amplify the signals. If you apply the signals, AC signals in the same way where V1 is equal to V2, it will not amplify. That will treat it as a common mode signal, right? For example, noise is there. Same noise is there both at both V1 and V2. Then that should be rejected. We don't want to amplify noise signal. The common mode signal should be rejected. Only the intentional signal. Intentional means, let us say, voice signal. You create the voice signal like a differential way, then apply V1 and V2. Between V1 and V2, then that will be amplified. But while giving the signal, actual signal to amplify, if there is a noise which is what is coupled to both V1 and V2, which is in a same way, which is nothing but common mode signal, that common mode signal should be rejected. We don't want common mode signal amplification. We want only differential signal amplification, right? Then let us say this is what is the circuit, this is what your differential amplifier. Take it, then don't disturb it, or I can say whatever signal you want to amplify. Therefore, before that we have to give common mode signal. I am calling this as common mode signal, the DC voltage. Here also we have to give the common mode signal VCM. Okay. Then whatever signal, then when I say this is what your VCM, some voltage, then you will get output DC voltage. This is what your output DC voltage. Here also you will get output DC voltage. Let me call this as output common mode voltage, VOCM. Right? Now, then whatever signal you want to amplify, then we need to apply AC signal on top of this. Therefore, the signal whatever you want to amplify, then we have to give it a differential way, then you will get it. But how will you get it? I will explain. Then you will get it something like this. Then what is this? This will be something like this. You will get it. Okay. Now take the circuit, but I'll explain. The blue one is nothing but the DC analysis. Then the red one is nothing but your AC analysis. That part I will explain. That is what is case 1 DC analysis, case 2 AC analysis. Okay. Take it. Take the circuit. I think I can say the time is over for this session. Now I think we have 3 more minutes. Within 3 more minutes, you try to draw the differential amplifier. Then in the next session, I'll explain how to get differential gain and how to get common mode gain, or how to reject common mode signals and how to amplify differential signals and without any capacitor. Remember, we don't have any capacitor. Okay? Take this. You can continue. The video will be played for 3 more minutes. It will be projected as it is. You can continue, try to draw within 3 minutes, else you can pause the video, okay? And then I'll continue in the next session, DC analysis and AC analysis. With that I can say differential amplifier is over, okay? Thank you.